Thank you so much. It's always great to be here. This is some work in progress with Stefano Antonini, Luca Eliasiu, and Patrick Tran, all at Berkeley. So this is still in progress, so there's still some pieces that we're still figuring out, but hopefully there's still enough that I can discuss with you guys and get feedback from you. So let's keep it as informal as possible. And I don't have to tell you guys, but please ask questions. Okay, so let's get started with the topic. So let me first discuss the setup. So let me first tell you what I mean exactly by long wormholes. So the familiar thing in ADS-CFT is, of course, the best known state is the thermofield double state, where we prepare it with a Euclidean path integral, length beta over 2. That prepares an entangled state of the two sides. The norm is computed by the partition function in 2 dimensions. It's just the disk solution. This is beta over 2. And when we cut it open on the slice, time symmetric slice, the Lorentzian solution we find is the two-sided black hole. This two-sided black hole has a very particular form of correlation. So at t equals 0, we have this slice, which is relatively short. So there's a few senses in which we mean this. So as you go forward in time on both the sides, then the wormhole becomes much longer. It looks something like this. And the length grows linearly with time, and so it becomes really large until you reach exponentially long times, and then there's corrections to that. So this is basically the time at which the correlations between the two sides are the strongest. You can probe this with mutual information or other correlation functions and so on. And so that's where it's shortest. There's another sense in which we mean it's a short wormhole, which is that there's a geodesic from the bottom end here to the top end here, which is marginal. So it's marginally traversable. You can almost get from one side to the other. You just about can't. But as soon as, so there's of course, the Gauss-Jeffreys wall protocol, which taps the two sides, sends in some negative energy and allows you to make it traversable. So it's just marginal, so that even a perturbative change will allow you to traverse the wormhole. So in that sense, it's a very short wormhole. Okay. How do you make the wormhole longer? So there's this idea called the Petz state. This was discussed by yes. Short for 2 reasons. I was basically saying there's strong correlations between the two sides here. And so you can prove that with correlation functions, etc. And it's like marginally traversable. So it's almost traversable for someone who left early here to get here. As long as you add in some slight negative energy shock, they'll be able to go through because of this traversable wormhole protocol, which you couldn't do if you were at really late times. Like here, there's no chance. Yes. Yes. Exactly. So as you move forward in time, the entanglement entropy doesn't change because the entanglement entropy of some state here is still given by the horizon area. It doesn't change. So that's why people often thought that this is related to some other feature which is not probable by the entanglement. So complexity was one of the notions which was introduced to say there's some sort of thing which has to correspond to this growing interior, and so perhaps it's this complexity. There are things you can probe. Like you can of course probe like two-sided correlation functions or like two-sided entropies, like Hartmann-Maldacena type surfaces, where you're computing the entropy of say an interval here and an interval here, and those will have basically zero mutual information or like small correlation and so on at late times, whereas they're like large at this point. So they can be in the connected phase at t equals 0, but they're in the disconnected phase at late time. So that's another sense in which there are some notions. So the full entanglement entropy of one side doesn't know about this change in the state, but the subsystem entropies do know about it.
There's some some smaller
Exactly. So initially you're starting from the state which is like e to the minus beta e over 2 e. So they're like very nicely correlated between the energy eigenstates. Then you start adding phases because of the chaotic nature. Like this is a very dense spectrum and it has a chaotic behavior, the correlations get lost pretty soon. Roughly, that's the intuition. Okay. Good. So, okay, so now that we have a short wormhole, let's discuss how to make the wormhole longer. So there's, of course, one sense in which we can make the wormhole longer, which is just go to late times. But what I'm going to say is it's a slightly different sense in which I mean a long wormhole, which this thing won't satisfy, but we can build other states which will satisfy. So that's where this idea of the PET state comes in. This PET stands for partially entangled thermal state. So this is some other state which looks thermal. So of course, the thermophile double is something that looks thermal on both sides, but it has some very particular nature of entanglement between the two states. This is something, again, which kind of looks thermal on both the sides, but it has a slightly different nature of entanglement between the two sides. This was introduced by Akash Goel, Hotat Lam, Verlinde, Herman Verlinde, and Joaquin Turiachi. It's actually interesting that this was, of course, discussed by Maldacena in 2001, right? It's a long while. And this is like 15 years later or something. It's very surprising that it took us so long to even think about this. Maybe people didn't think it was interesting, but anyway. So here the idea was you can deform this thermophile double in the particular way, which is this visible? Yeah, okay. So you can do the usual thermophile double thing, but now instead you add in a heavy operator. Let's call it O. So you add a heavy operator. The action of this is, of course, to insert some energy. So this inserts some energy, which if it's heavy enough, it basically follows a geodesic in the bulk. So when we compute the norm, draw it slightly differently. So in 2D gravity, we usually draw it this way. So in JT gravity, the solution that we have for these boundary conditions where you have no sources is, of course, just the hyperbolic disk. So here, because we have this energy shock, which is following a geodesic, what we do is take two pieces and look at some geodesic and glue them across this geodesic. Glue them across this geodesic and there's a matching condition dictated by the mass of the shell. So we have some deformation of the thermophile double where we added in this source, and now if it's heavy enough, then it looks like this, where it sort of pulls in the two boundaries where the energy is, and the structure of the state at t equals 0 looks as follows. You have a horizon here and a horizon here on the t equals 0 slice, and there's some matter in the middle. So if I look at it in Lorentzian, it looks like the following. It looks like a long wormhole, a longer wormhole than the thermophile double, where there's two horizons and there's some matter shell here, which was introduced from the Euclidean past. Okay. Good. So in this case, of course, it's clear that, so what's happening here is that because you've added in this matter shell, it's increasing you can think of this as an insertion of something like e to the minus ml, where L is this length. Let me call it L1. So let's say this is L1, and the length of this slice is L2. So what it's trying to do, if you insert e to the minus ml1 into the path integral, it's going to try to make L1 shorter if m is large. So it's trying to make this shorter, and the effect of that is to make L2 longer. So it's making the wormhole longer. Correct. Exactly. It's the opposite of that because, yeah, exactly. So now here on this t equals 0 slice, the correlations are much weaker than you have in the thermophile double. So if you can probe it by, again, mutual information or some correlation functions and so on, and it's going to be much smaller. Okay. Yeah, this solution is very universal. It's not particular to 2D. It's spherically at least spherically symmetric. It basically looks exactly the same thing. The Penrose diagram is literally that. You can construct them in higher dimensions as well. It is, of course, in this geodesic approximation where you're thinking that it's a heavy enough object that's following a geodesic, and you're just using matching condition.
But you could presumably make up the
Yeah, I think you can smooth this out and get something with a scalar field or something like that. So this is what these guys called it. It's what's a partially entangled thermal state. So it's like kind of thermal on both sides, but it's less entangled than the thermophile double in this particular sense. Exactly. So good. So there's one difference between the long wormhole that we have here and the long wormhole that we had here in the thermophile double at late times. So yes. Here I think you just assume that it's like dust. You can have other things, but yeah. Like a brain. I thought you could have this also for yeah, for dust for sure this exists. I thought it also exists for an end of the world brain, like it's kind of like a B state, right? Like
So the difference being that the dust has only energy density.
yes, and this has pressure. Yes, yeah. Yeah, I thought it exists, but okay, I'm not sure. Like, isn't the Hartmann-Maldacena construction of this B state in 3D gravity, and it's like you essentially think of this, but without this side, right? Like you can just double that and get this picture. There's no physical difference between them. Oh, I see, I see. So here it was kind of, I mean, here I was assuming this is in the middle, but maybe you're saying if you move it, like if you have perturbations to this, you're saying maybe it doesn't exist. Different temperatures. Okay, okay, okay. I'm not sure of that. Okay, that's possible. Yeah. Good. So the difference between these two is the following. So if I draw the slice at late times here, it just looks like you have some boundary on one side. It's a really long cylinder, and it goes out to the other side. That's what the Einstein-Rosen bridge looks like at this late time. Here, on the other hand, at t equals 0, it looks as follows. So you have a large boundary. The area decreases as you go inwards. You hit the first horizon. That's a minimum of the area. The area then grows again until you hit the shell. And then around the shell, side of this. And then again, it shrinks after that, hits a throat at the horizon, and then grows outward again. So there's a minimal surface here, there's a minimal surface here. So these are the two throats, the horizons. And this is a bulge. So it's a maximum of the area. Yeah, in 2D it's dilaton, or in higher dimension it's the area. Yes, correct. Any heavy operator will do the job. Like so here we're imagining it's a local heavy operator in 2 dimensions. No, it's in Euclidean, so you can think of it as acting on either, right? Like so here the state that you're preparing is, so if this is, it's going to be a two-sided operator. Like it's because it's acting in the interior, it's some complicated combination of these two. Like you can represent it in different ways. So let me write this down. So this operator is going to be, and let's call this O. Then this is like e to the minus beta L H O e to the minus beta R H. That's the operator we're considering, and then you can think of like do the usual thing where we flip Browse-Stokettes and think of it as a state to get this pet state. So you can like if you started with the maximally entangled state, acting with this operator will give you the correct state. So you can think of this as acting on the right, this on the left, and this either, like it doesn't matter. You can act on either of the sides and it will give you the same state. But this is some complicated operator. In 2D, yes, it will be just along the geodesic. In high dimensions, it will be like a spherical shell. Codimension one, correct.
The one-sided optical would just be the state one.
For sufficiently coarse-grained observables, yes. Because so you can imagine tuning beta L and beta R. So this need not be exactly Z to symmetric. Then these areas will be different. So one of these will be slightly larger. Let's say this is slightly larger. Then the entanglement wedge of the right side will be all the way till here. So it includes the shock. So the right side can then probe all the way up till here. This is entirely in its entanglement wedge. They can probe that. With simple observables, you'll still just see like coarse-grained like thermal state. And similarly, from this side, you'll only ever see the thermal state. But with complicated enough operators, you can probe this region.
So bit of change in temperature would
Yeah, I mean, even in the other case, in principle, they can, either of them can probe it. There'll just be errors because it's this degenerate case where there's two surfaces. So the middle region is not sharply in one entanglement wedge or the other, it's in both. So that's like a degenerate situation. So let's think of either it being one side or the other side.
confirm becomes the
Yes, there's a phase transition, exactly. Okay. Good. So the distinction here is the presence of this bulge. This is what in this literature is often called a Python's lunch, because they thought this looks like a Python who's just had a lunch. And the idea was, so this is a paper by Susskind, Pennington, Brown, and Garibian. Their idea was that there's some notion of complexity growing here. And the complexity growing here is this growth of the wormhole corresponds to the growth of the two-sided state becoming more and more complex. But here, this Python's lunch is an indicator of something else. It's an indicator of the fact that one of these sides can probe this region, but in order to do so, they have to implement a complicated operator. So it's related to what Abhijit was asking, which is if they only probed with simple operators, they would only probe this outside region. But in order to probe this, they need to act with complex operators. And these people estimated how complex it needs to be and so on. But the general idea is as long as there's a Python's lunch, then you have to do more complicated operations to access that region. So the difference between these two situations is the presence of the lunch. For me, a long wormhole is going to be, yes, it's going to be a situation with two horizons, but more so, it's going to be one which has a very big Python's lunch. So in this case, it's big. I'm going to make it bigger. More operators, yes. Yeah, exactly. The one with the higher temperature, lower beta. Yes. The higher temperature means you have access to more states roughly. So your horizon area is much bigger than the other side. And so you're able to access this because of the larger entanglement between your exterior region and this interior region. Okay. So this was the PET state, which is a long wormhole. Now let's build longer wormholes, as Omkar was saying. What we're going to do is add more and more operators and build something similar to this. So now we have, again, something like the thermofield double, and we add many operator insertions, each of which produces a large amount of energy. They all fall into the bulk, and the corresponding Lorentzian picture is a much longer version of this. Where again, you have two horizons. And now we have 1, 2, 3, 4, 5, 6 of these shocks. And if these are heavy enough and there's like sufficient spacing between them, so there's two things we can do. We can work in the canonical ensemble where we fix the amount of Euclidean time evolution between these shocks. Or we can also fix the energy, in which case the Euclidean time evolution just adjusts so that you get the correct energy. So more of what I'm going to say is going to be relevant to the microcanonical case. So let's just think of that situation where we fix the energy. Yes. How do you know that this horizon is here? Yeah, that only happens if the operator is heavy enough and this beta L is large enough. So if you imagine like adding the operator here, it's just going to be something in the exterior and you're not going to get to horizon. So there is some point at which that starts happening. So we're considering a situation such that that happens. I think it's a function of the energy. So it's not like, yeah, it'll be a theory dependent thing.
What would be like
In that case, I think it'll just look like it's just like the thermofield double, but yeah, with some stuff on the left. So it'll just be like symmetric scenario. No, I was putting it very close here so that there's a transition. No, I think if it's symmetric, there's nowhere for it to go. Like it has to be in the middle. Yeah. So if the situation was if it's very much on one side, then it sort of looks like that, with this stuff on which like comes out of it. Like making this symmetric. So you have
that will not happen.
yeah.
It would have
Yeah.
That was the.
That needs like negative. Yes. Correct. Yeah. Yes. Yeah, I can. Yeah. Yes.
The first constriction is simple operator.
Is simple operator.
But thereafter, till the second constriction, you go past the bulge, all the way to the second is all complex.
Yes. So
There's something called.
yes. So let me just briefly explain that. No, that's actually an important part. So let me just say that. The idea is, how they came up with this proposal is just thinking about tensor network models of this. So you can imagine a tensor network, which is big on one side, then it shrinks, then it has a bulge, then it again has a throat, and then it grows outside again. And just from entanglement wedge reconstruction, we abstractly know that since this is the true RT surface, everything to the right of that can be reconstructed by the right. That's an in-principle statement. But in order to do it, what you need to do is basically, you need to sort of invert the tensor network. So you need to access, like remove all the tensors, act with this operator, and then come back, right? In order to do that, it's fine as long as the tensor network is growing. If the tensor network is growing, then there's an isometry from the smaller surface to the larger surface because the dimensions are growing as you go out. That's the part which is outside. In the outside part, that's happening always. And so it's very easy to just build outwards from that. But here there's a part where you grow outwards and then you have to shrink. Shrinking means post-selection in the tensor network. So you're like reducing the number of legs, which means you have to post-select. And post-selection is a complicated thing. You can't do that with a simple operation. You either like keep trying until you get the right answer, or there's some smarter ways you can do it. But it's that is something that introduces exponential complexity into reconstruction. So that's roughly what the idea is. Yeah. So it's because of the size decreasing that that's representing some post-selection in the holographic map.
For example, of the Python, which would also be the vacuum.
Oh yeah, vacuum state 2 intervals has a Python lunge. Exactly. So in the vacuum state, like Abhijit was saying, vacuum state, if you have 2 intervals, there's 2 surfaces like that, and the Python's lunge looks something like the X. Okay. So here we're imagining we have K insertions. We're thinking of all of them as heavy. I'll later discuss what happens if they're light. They could also all be the same or be completely different operators. We can consider many different situations, and I'll talk about both of those situations. So once you prepare this state, then here what ends up happening is you have many new extremal surfaces, as Omkar was saying. All of these are minimal surfaces, and all of the matter shocks are basically bulges. So you start from here, it goes down, and then it keeps growing and shrinking over and over again. It's like a sort of oscillating slice, something like that. Where there's matter shocks everywhere here. Yeah. Yeah, so you can tune many parameters. So here, like, there's a lot of freedom to play with this. You could make it such that, say, this one is the minimal surface. So then everything to the left is reconstructed by the left, everything to the right is reconstructed by the right. So it's going to be dictated by the minimal surface in this. So there's many things you can play around with here. And you can also change the size of the bulges and so on. And there's a formula for how much you expect the complexity to be. So it roughly just ends up depending on the drop. So how much you decrease. So the post-selection amount of post-selection is controlled by the difference in area between a bulge and the throat. And so it's the total complexity is basically going to be dominated by the single largest drop because it's exponential in that. Yeah. Yeah. In this example, I think actually the simplest example is this. This is much simpler because this X is kind of weird. Oh, in this geometry? Yeah, I can draw, okay. Maybe I'll just write here. So the tensor network we're thinking about there, okay, let me bring this down actually. So just imagine discretizing this. So we're just drawing some network like that. Something of that sort, where here there's a throat. So let's say there's just two legs. Something like that. Okay, and then it grows. So now the number of tensors is bigger and bigger. Each of these is isometry. So as long as you're going from a smaller number of legs to a larger number of legs, that's an isometry. So as you're going this way, it's all good. Like this is a simple thing to build because you imagine that you know all of these isometries and you can build up that part of the network until it gets to this point. But then you get to a point where there's still many legs, but now these tensors are going to contract. So there's going to be less number of tensors on the next level. Something like that. So you're going from a larger number of legs to a smaller number of legs. And that means if you think of that as a unitary, then there's post-selection because you went from like 2 legs to 1 leg. That means you had another leg, but you post-selected on it. That's the idea. Whereas in the other case, it was just you feed in something and you get 2 legs as an output. It's projection. It's basically, I mean, in quantum mechanics, of course, like projection we use as a substitute for measurement, but really you think that you do this experiment with some probability, you get this answer. Of course, here these bonds are like huge dimensions, so you have to do this experiment many times, like an exponentially many number of times to get the right answer. And so that's why it's complex. Sir? Oh, yeah. Yes, this one. Yeah.
It also is because whenever you insert operator on the disk, like it's a question of how you slice the disk, how you cut the state to.
I mean, there's going to be one saddle point for where that surface is going to lie. Yes.
So you take that into the correlation of the boundary and then you look at the complex time will it show that is that what it means?
Can you say that again?
When the operator is too close to the slide.
Yeah, whether it's this or this. No, sorry, why? No, but there's a saddle point for it. That's what what I'm drawing here is the saddle point geometry, where the most likely place where the geodesic lies. And then it's a clear question of whether the horizon is out, like whether there's an extremal surface here and here, or whether there's only one extremal surface. It will show up. No, they will. Like if you, for example, here, if you computed some 2-point function. Oh, one-sided correlators only see the exterior region. Yeah, that's right. One-sided simple like when we say correlators, we usually mean like 2-point function, 4-point function, whatever. If you have some complicated operators, then you can probe this region as well. No, not like, yeah. I mean, if you just probe like 2-point function here or something, it will just see the exterior. Yeah.
Following on the matter.
Yes.
When you have the matter there, you've got a source here and a source.
Yes, so there's a source in the state has that. So there's one in the ket and one in the bra.
Along with going asymmetrically moving
Yes, correct.
So that's not just one point.
Oh, that was the question. Sorry, now I understand. Okay, sorry. Sorry, yeah.
You want to analytically control Lorentzian, you have to.
Yes. I want it to be a time symmetric situation. Yes. Correct. Sorry, I didn't understand that. Okay, so in the end, what we have is this sort of long wormhole where we have, so we had k operator insertions. Each of the insertions corresponds to a bulge. So there's k bulges. Yeah, exactly. And like regular meals, guess he's pregnant or something like. So k plus 1 extremal surfaces separated by this. Or the Python has constipation. I don't know.
It's just one Python plant.
Yes.
Any Python plant.
Yes.
It's the same
Exterior sort of.
same length of wormhole.
Yes, I think so. I think it should be possible. Yeah.
That entanglement kind of complexity or whatever it is between the two, don't really see that.
You're imagining.
Theory possible.
Yeah.
How you would see the difference?
Okay.
Very good question. What is it?
So I guess you're imagining like one of that type of geometry.
Which is a lot of it is it's called R,
Yes.
and many of these which are called the same. Length. Yeah.
The length is the same.
That would have, if you take the same operator and break it into two and keep it in the middle, right?
Yeah, that sounds right. Yeah. Okay. If you just split this and made it two operators.
From politics, of course, very.
Yes.
There was one thing, what field, the field theory, how it is.
I would think that two-sided correlation functions would see that. But how? Yeah. I mean, like. It passes it, but I guess the length is the same. So like e to the minus ml is the same. Like in that, but yeah, then it can sense that, I guess. Oh.
Recreation of these, into the thing.
Yeah, you do
Between complex operations.
Then of course. But it's
Like a field theory, like yeah. Yes.
It's not the same.
It's not the same geometry. I guess Shiraz was asking if you just fix this one parameter, which is the length, then in some approximation, at least the correlation function seems similar. Once you start sending signals, like, yeah. Much more. Well, I guess we're working in some. Yeah, I'm not actually sure we have enough parameters to make this work because, yeah, we want to hold the energy fixed when we're saying this so that the exterior looks the same. Otherwise, we can just see it from the exterior, as you're saying. And you want to hold the energy same and the length the same, while also splitting it into two parts. It's probably possible. I don't know. Yeah. Every time you cross the shell. Yeah, I think that's like what related to what I was saying. You have to move in time to see that, I guess. But then the geodesic just like, it doesn't have a kink at the shell, does it? Oh, it does, you're saying? Oh, maybe it does. Like, I guess you're imagining that if you have some something here, then no, this is a geodesic, right? Yeah. Yeah. Oh, I see. In JT. Okay. So you don't see it from the geodesic approximation, but you see it from this more detailed calculation. Okay.
2-point function.
2-point function.
One here and one.
Yeah. Oh, that sounds right. Yes, yes, yes. Oh, yes, of course. In DSSYK, it's true because there are different number of crossings. And yes, correct, correct, correct. Is heavy.
So I can think of it as like the geometry patch. Like
Yes, yes.
then it's not indirectly computed, something like that. So you can yeah.
Yeah, I mean,
You don't have to match across the mark.
but that's what I was asking. Isn't this just a geodesic that's allowed? Like, so I think it's different than that, right? Like, I thought it's a different effect. Yes, yes, that I agree with. Yeah, yeah.
I mean, I think, as you say, that not regarded that how they have heavy operator.
But then always a very heavy operator that is modify the geometry. Then you move on this geometry.
That does sound right. Yeah. Okay, yeah, I'm not sure. I'll look into that. Okay. Good. So now we have this situation where we have K bulges because of the K insertions, and they're separating all of these throats. So we have K plus 1 throats that are separated by these K bulges. Okay, good. Let me move here. Okay, so the reason we got interested in this was because of a particular special case that was discussed by the authors LMRS, Lin, Maldacena, Rosenberg, and Shan, where they looked at these BPS wormholes in n equals to super JT. Sorry, was there a question? Yeah, so the construction there is pretty similar. Their idea was essentially that instead of having, so here we had some finite beta or some finite energy, and here instead you want to look at the ground state. So in this n equals 2 super JT, the spectrum looks as follows. You have a BPS sector at 0 energy. So the density of states has this form. There's a gap, and then there's a continuum of states beyond that as a function of energy. So what they were suggesting was to zoom into this BPS sector and look at different possible states that you get there. And the way you construct them is essentially the same idea, but instead of looking at the thermofield double with finite beta, you look at the thermofield double with a beta going to infinity. So that will project you down to the ground states. Then you can run the same story. You can again find a longer wormhole by adding an operator that will increase the energy, but then you cool it down further by an infinite beta again, so it will bring you down to the ground state. That's going to give you a geometry very similar to this, except now it's a BPS wormhole. So it's an actual supersymmetric state with this matter insertion in the interior. And similar, the same story holds here as well. So you'll get some other geometry of this sort, but because you've taken beta to infinity, you're guaranteed that this is a BPS state. Yeah, both. Yeah, all temperatures tend to infinity. The length.
I just take one lump or I divide it into two.
Yeah.
The total length is not conserved. It depends on how you distribute the mass, because the geometry cares about the redshift factor locally as you cross it.
So this is while trying to hold the energy fixed or something?
So if you have some amount of mass inside.
Yes.
Dividing.
But when you're dividing into two, I guess you're saying just like separate them by some particular Euclidean
some distance.
Euclidean distance.
Okay, anyway, it's on the side, but this was the gravitational fact. You cannot get it. I don't think you get the same. It's the dilettante. So let me define boundaries to be where the dilettante is some fixed value, right?
It sounds like, it feels like we have enough parameters to make it work though. I mean, that's why I'm confused because you,
In a time symmetric slides,
yes,
parameters of that is a term.
yes, yes, yes.
The geometry inside care about which mass.
Yes. But since we're allowed to, so now I'm allowed to change the masses as well, right? Like we don't need to fix like these masses need not be half of the original mass or anything. That's a parameter in hand. And so we can make sure that the matching condition across this is such that it has the same length. I feel like we have enough parameters to do that. It may not be just from splitting the exact same mass. So that I agree with. There's some detailed thing, but the counting of parameters, I think, works out. Yeah. No, thanks for the question. Okay. So in this context, yeah, we have this infinite Euclidean evolution. And so again, something like that. We have an operator, let's call that O delta. And then we have an infinite amount of Euclidean evolution on both these sides. Good. So this is basically like acting with this operator, O tilde. Yes, I think it's that fixed R charge. Yeah, that's on. Yeah. Yeah. So this operator O tilde can be thought of as a projector onto the BPS state times some local operator that's heavy times PBPS. So you act with something, then you act with this projector to cool it down, and these PBPSs are implemented by limit beta goes to infinity of e to the minus beta h. In the supersymmetric case, it actually approaches a finite length. It's kind of a funny. In the JT gravity, it's not a good limit.
So the whole thing will become large, right?
The black hole becomes tiny. The black hole becomes tiny, and the length becomes really large. Yeah, maybe which one did you mean? The area becomes really small because the entropy is becoming smaller, and the length becomes really large. It's almost like factorizing the thermofield doublet.
Right. So that would happen if you do it with the operator, then that would just kind of factorize.
Yeah. Yeah, it's not a good limit, so I'm not sure you can even trust the semiclassical picture there. But if it was, say, just large, not infinite, then I think, yes, it would be like a really long wormhole with this thing cut in the middle. The correlations are really weak between the two sides. Yes. But in this particular case, it actually approaches a finite length.
Finite length.
Yes. No, because you have S naught, a large number of states at zero energy. Yeah, that's the particular difference.
So here you're going to now take the beta.
Yeah, it's basically the same thing I was saying, but now we're working with super JT gravity where this beta goes to infinity limit makes sense, and we talk about that. It's not really important. All I was trying to say was this is where we got motivated for it. This problem that I'm going to phrase came from this paper. That's all I was trying to emphasize. Okay.
From this, I remember hearing one day they had talk to a
Yeah.
I don't understand what the point is.
I think, okay, that paper is like, they tried to do a lot of different things, a very confusing paper. This part of it, I think they were trying to emphasize that here, whatever configuration you get after adding these energy, like these insertions, in the end, we're guaranteed that it's a BPS configuration. And I think the thing they were trying to point out was even if you have all this crazy matter, which need not themselves look very supersymmetric, the overall configuration is still BPS. That was sort of part of the point.
Yeah, so I remember you were saying that there was more information than the number of supersymmetrics.
Good. Yes. Oh, let me get to that. Yeah. That more information is exactly these operators. So this one of the interesting things that paper did was focus on these operators. These operators are just like some heavy operator projected down to the finite dimensional BPS subspace. And their point was that there's some feature of chaos even at zero energy. So because like the chaos bound naively puts a bound on the Lyapunov exponent, which is 2 pi over beta. When the beta goes to infinity limit, it's a trivial bound. There's no chaos. But what they were trying to say, or this was taken up later by Schenker, Lin, and Chen, that there's still chaos that you can sense by looking at these operators. So when you look at these operators, their eigenstates. So this is a very simple operator. It's a simple operator which at high energy is just some local conformal primary or something. And but nevertheless, once you project it down to the BPS sector, it has a very chaotic spectrum. It looks like it's an RMT-like spectrum, and it has random eigenvectors. That's where the chaos is hidden, even in the BPS sector. That was part of the idea. Yeah. Pure, yes. Pure n equals 2 super JT has a, and even n equals 4, I think it has a random matrix theory description. When you add in matter, I think it's not understood. Just like JT plus matter is not understood, this is also not understood, but it's believed that there is a random matrix description. Yes. That is chaotic. Exactly. I think that's partly what motivated them. So they looked at like SYK as a model for this and found that chaos was there. And SYK itself is described as some sort of random matrix-like statistics, even at these low energies.
From n equals 4, not surprised. I mean, just the one loop Hamiltonian on the n squared thing looks like it could have very active.
Because we are not probing chaos in the same sense. The 2 pi over beta is probing chaos in the OTOC. It's probing chaos it's the Lyapunov exponent of the OTOC. So there's no chaos in that sense, but there is chaos in this sense. There's eigenvalue repulsion, random matrix statistics, random eigenvectors, and so on. These are operators that aren't simple boundary operators, right? Like once you've done this projection onto the BPS sector, they're like far in the Euclidean past. They won't look like particles going and falling into the horizon. If you take this state and now act with an operator, then you'll not see any chaotic behavior in the OTOC. So if you like the OTOC situation is usually you have this Lorentzian situation and then you want to probe it with some simple operators on that background. That won't have any chaos because of this trivial Lyapunov exponent. But there's still chaos in some other sense. I think partly their motivation was they wanted to say, like, one of the complaints about, say, fuzzballs and stuff is like it cannot capture this chaos aspect. Like the horizon is really important for getting, say, the chaos bound and so on. Like they're very universal features of the horizon. So if you get rid of the horizon, you lose that. But then you could say, oh, but fuzzballs are at zero temperature and chaos bound is trivial. So what sense are you even talking about chaos? And they wanted to say there's still some sense of chaos that we still need to capture. This was then later emphasized by Schenker and others, that you still need some feature of chaos, which if you believe that fuzzballs are the right sort of microstates, then you need to show that they have this sense of chaos. Okay, good. So for example here, if we take delta to infinity, they'll take delta to be really large, then we can look at what the spectrum of O tilde is. So if we compute moments of this, so let's say we compute trace of O tilde delta to the 2n, that's basically given by a circle with 2n insertions. I don't know if it's even, but whatever. And then now you just consider all possible contractions between these different operator insertions. The important point for the delta goes to infinity limit is that anything that crosses is going to be suppressed. So for example, a diagram of that sort is suppressed because of the gravitational interaction at this point. So because delta is really large, this term is highly suppressed. It basically is like a Euclidean version of the OTOC, which is highly suppressed compared to the diagrams that don't cross. So all these crossing diagrams are suppressed, and you're left with diagrams of this form. No, I'm just representing like Yeah, you can think of it as geodesics because here it's a heavy operator, but more generally, I just meant like propagators between those 2 points. So it's the time ordered propagator versus the out of time ordered propagator, like which ones you're gluing together. I just mean that like if I had this one, then here, yes. I just mean so. Yeah, this is so. I just mean that here, what's happening is, this propagator is influenced by the presence of this insertion. In that sense, it's out of time ordered. So there's a gravitational interaction coming from this presence of this. On the other hand, in the other diagram, this thing is completely independent of this thing. That is the analog of the time ordered thing. Yeah. I just want to tell you about in what sense this operator has a random matrix spectrum. Yeah.
Sorry, and that this
I'm going to say that. I haven't got to it.
that this is better than the other, just that the length, these are smaller tokens.
Exactly. Whenever you have like if you think about this picture, like once you have this insertion, the correlation between the others becomes very weak because that length becomes larger.
But I was asking just the length of the geodesic, the sum of the length of the geodesic. This is better than that. Is that?
No, that's not true. That's not true. It's because of the interaction there. Sorry?
You have geodesic in the right geometry.
Yeah, in the back reacted geometry, you can say that. Yes.
But it's not what I
Yes.
Okay.
It's because of this notion, the thing that we were saying here, that if you have one of them, it brings this together, but it sends those of it. So then those become weaker. Yeah. Good. Okay. No, any in this particular situation, any non-crossing diagram contributes the same. Good. So now we have all non-crossing diagrams, and so this is just given by. So there's a contribution that comes from just the disk, is just from the genus counting. That's e to the s naught, and then there's a factor of all these propagators. So here there's no position dependence left at all. It's just some number. So we have some propagator to the power of n, where it's coming from n different pairs, and then the yes.
You say that straight over. You've chosen to pair to itself.
No, because it's O tilde delta, it's always separated by infinite Euclidean distance.
These two infinities are the same.
Which one?
You made it uniform.
It's infinite.
Yeah. Okay. Couldn't one be twice the other? Or,
Oh.
yeah.
You're saying like the ratio can affect the answer? I think it doesn't because, yeah. I think it doesn't, but I'm not. Yes.
So then maybe it doesn't matter.
This is certainly not what you would find if it was JT gravity. That's definitely true. It's just that in the BPS thing, this propagator has a beta goes to infinity limit, and all of them are basically just given by that. But maybe that's not a perfectly satisfactory answer. Yeah. Yes. From the because it's just this operator, right? Like this operator is a well-defined operator. Yeah. Thanks. Good. So we have factor of e to the s naught from the disk, n propagators, and the more important factor here is the counting of these diagrams, which is given by the Catalan number. So this is the number of non-crossing chord diagrams here is the Catalan numbers. The Catalan number is defined as follows. P is just the propagator, so it's just some factor that comes from this. It's completely, yeah, independent of anything. It depends on delta maybe, but we also send delta to infinity. The Catalan numbers are given by this 2n factorial over n plus 1 factorial, n factorial. This is some standard combinatorics number which shows up in a lot of places. It shows up in random matrix theory in particular a lot. And that's basically because whenever you compute moments and you find that they're equal to the Catalan numbers, that means so you can invert that and find the spectrum. And the spectrum of this O tilde delta, so lambda, rho of lambda, looks like a semicircle. So it's this semicircle, it's the standard Wigner semicircle. So it is the spectrum of O tilde delta. So it's because we send delta to infinity. In the large delta limit, it'll become this. What is what? P to the n. P is just like the propagator between these 2 points, and is the same for all of these. They're all separated by infinite Euclidean distance. So you're just getting a factor of P for each pairing. But P just depends on delta, which we're sending to infinity anyway. It's just some overall factor. There's some renormalization. Like this one, for example? Yes, yes. Like this doesn't play any role in that. They don't interact, basically. Okay. So this is essentially showing you in what sense you have chaos here. Like, so you have this Wigner semicircle, which is very characteristic of a Gaussian random matrix. So this O tilde delta essentially behaves like a random matrix, Gaussian random matrix. For more general delta, it won't be a Gaussian random matrix, but you still expect, there's an expectation that it still behaves like a random matrix for some other potential. That hasn't been made clear, but it's just, it was proposed by this BPS chaos paper. Okay. Good. Yes. So that's again, so it'll again depend on the details of delta and so on. But in the delta goes to infinity limit, as long as these, so if you have two different operators which are chosen like freely independently, then it'll again be given by like free probability, and it'll have this random matrix behavior. Well, it'll only depend. So I'm assuming that the 2-point function of O1 with O2 is 0. So I'm only considering big contractions between O1 and O1 and O2 and O2. Then there'll be factors of the propagator between them. So there will be some dependence, but we're sending both delta to infinity. The combinatorics is interesting, and that's completely given by free probability theory. So it's the same thing you would use if you had two random matrices which were freely independent. So it behaves just like that. But yeah, that's what I meant. Okay. Okay. Good. So that was the setup. Oh wait. Good. So now let me get to the puzzle. So the puzzle is the following. The puzzle comes from trying to compute the entropy of one side in such wormholes when you have all of these insertions added in. It won't matter either. So you can either be in the supersymmetric case or in the microcanonical ensemble in the general case. Like this is a very generic thing. They pointed it out in the supersymmetric case, but we basically realized very general. So it's not particular to the supersymmetric case. Finite beta is fine. It's going to be important that you're in the microcanonical. So essentially the important feature is going to be that you have a finite band of states that you're looking at. That's the important feature. Yes.
So you're on one or the other boundary.
Yes, you're computing the entanglement entropy of one side with the other.
Okay. So shouldn't I be looking at some minimum area?
That's what you would do classically. So let me say what happens if you do that. Yes. So you can do that. That's going to be a sensible thing to do, at least here. There's going to be some problem with that, which I'll point out. The basic problem is here, if you're fixing the energy, or even in the supersymmetric case, what ends up happening is all of these areas are basically degenerate. So you have many degenerate RT surfaces. And so you have to account for that fact. So of course, at leading order, the answer is just given by the area of that surface. But there's some other contribution that's coming from the fact that there's many such surfaces. And so there's some fluctuation in where the surface is. That is not going to play that much of an important role. Like bulk, maybe there's some sense in which you can think of this as a bulk entropy, but bulk matter is not going to play much of a role, other than the fact that it's creating this long wormhole type situation. Good. So that's a easy case that we're going to consider just for analysis. The problem should be more general than that. In the supersymmetric case, that will end up happening just because you're always projecting onto zero energy. Or even if here you project onto fixed energy, then the energy, so these extremal surfaces in the middle are basically the horizon, the would-be horizon of that energy. So they're all going to be the same if you fix the energy to be the same. We can be in a slightly different situation, and I think you'll run into similar issues as long as the total band of states is finite. Good. So for now, let me first consider the case that they considered, which is the supersymmetric case where you can take O tilde delta. So let's create a wormhole of this sort with all of the operators being the same. Yeah. Yes. Good. That's because the response is symmetric, right? So here you could say, like, if I start from here, this has to add in some energy, so this energy should be more. But you could say the same going the other way. Yes.
So if you have several of them.
Yes.
Starting from one end, your electrons will.
No, because like the way the geometry is responding is very symmetric. So what's going to happen? It's just a cut and paste thing. Like they're going to take pieces of the disk, glue them together, and you'll find a solution of this form where it's just the same disk everywhere. Like it's the same value of the dilaton at the horizon. Yeah. Okay. So now the state that we got is created by k insertions of this type, and let's take them all to be the same. So let's say it's all O tilde delta. Then the state on one side is basically given by O tilde delta to the power of 2k. That's coming from basically thinking of the Euclidean path integral, where we trace over one side and we have open boundary conditions on the other side, and then we had k insertions in the ket and then k insertions in the brown. Is the it's this thing. It's the BPS projected O delta, or in more general case, the microcanonical. Yeah. Okay. Good. So now let's try to compute the entropy of this particular state. So yes. No, in the BPS case, it's all infinite.
Yeah, but in this.
No, I'm talking about the BPS case right now. It doesn't matter. In that case, you could adjust it, but we're using fixed energy boundary conditions. So the beta will adjust itself to make energy constant. So it's not a parameter we have in hand. But here, I'm just talking about the initial puzzle that was pointed out by LMRS, which is in the supersymmetric case. But we can also talk about the microcanonical case, and it's the same sort of thing. Okay. So exactly. Yeah. So you're always going to have projections, and yeah, it's always going to put you in the same energy band, and like the beta is going to adjust to make the energy the same. No, it is correct. As long as the projector is on a like order 1 window, or like what you usually do in thermodynamics. Like if you don't make it exponentially small, then you'll have this sort of a description. It's cleanest in the BPS case because you don't have to specify a window and all of that. That is why they consider that situation. But in the other case, there'll be some dependence on the size of the band. Okay, good. So now let's compute the Renyi entropy of this. So the Renyi entropy is defined as follows. It's log Zn over Z1 to the n. Zn is just trace of rho r to the n. Z1 is just trace of rho r, whole thing raised to the power of n. Okay. So good. We've computed each of these things. So Zn, so remember that so Zn is just taking this and multiplying it n times and then taking the trace. So that's just trace of O tilde delta to the 2kn divided by this thing was just trace of O tilde delta to the 2k, whole thing raised to the n. And we already computed both of these things. It's just given by this e to the s naught times the propagators times the Catalan numbers. So this thing just becomes 1 over 1 minus n log of e to the 1 minus n s naught. The propagator factors cancel, and there's the Catalan numbers of kn divided by Catalan number of k to the power of n. Okay, so it's just coming from the previous expression. So now you can, now let's think of a situation where we take k to be larger and larger. Then there's an approximation for the Catalan numbers. The Catalan numbers of kn approximately go like 4 to the kn over kn to the 3/2. This is just from the asymptotics of the Catalan numbers. Yes, yes.
Why that expression?
Yeah.
Is that kn?
Yes, because we start with this. So this thing is just trace of rho r to the n, right? So rho r is this. So rho r to the n is just O tilde kn. It's just that. Yeah. So rho r is just this thing, right? So we had the thermofield double with k insertions. Then we trace it, and that gives you another k insertions, and we have open boundary conditions on the other side.
You are computing with disconnected correlator.
Disconnected. Oh yeah.
There you are just doing this disconnectedly. That's
Yes.
why you have this power. But
Yes.
you do not have a connected saddle.
Okay, I'll get to that. But this is the naive thing you would do at the disk level. Like this is the semi-classical thing you would do. Like if you just think of applying the usual Lucas-Maldacena type thing, this is what you would do. That's so the wormholes are going to be important to the story. Yeah. Yes, I mean it's 2k because I had k insertions in the ket, and then the bra will have another k. So it will end up being positive, but for that reason.
And it's just 2kn because anyway it was infinite length.
Oh yeah. Or you can just manifestly see it from this. Either way, yeah, correct. Okay, so if I use this approximation for the Catalan numbers, this thing is approximately equal to the following. It's S0 minus 3/2 log k plus small corrections. This is at large enough k. Okay, so what you see is if k becomes much bigger than e to the 2 S0 over 3, there's a chance that the entropy is becoming negative. So a naive extrapolation of the disk answer gives you a negative entropy as at large k. So the general tendency for this thing, so just to give an intuition, as we add more and more k, we saw that the wormhole gets longer. The areas, of course, are being the same. So the RT formula doesn't see the fact that the correlation between the two sides is getting weaker. But the actual entropy that you get from doing the full Euclidean calculation does see the fact because of this this combinatoric factor gives you a reduction in the entropy. So as you increase k, there is actually a reduction in the entanglement entropy, even though the RT formula at leading order doesn't see that. If when k starts becoming really large, then you start seeing that. Okay. Yes. Because the RT formula will just give you the S0. So each of those areas is basically just going to be S0.
But is there a way to see this in this more fancier formula?
Which fancier formula? No, this is well, okay. Maybe one way to interpret it is that this is just the classical piece, and there's some quantum correction to it from this thing. You can think of that because in some sense, this counting is coming from a one loop piece, right? It's coming from the propagators contracting and so on. So you can think of that as some matter partition function in the bulk that's giving you that piece, and that's giving you the reduction in entropy. But yeah. So you can think of it as an FLM piece.
Oh, and how many different, are there many degenerate extremal surfaces?
Yes.
K different things.
Yes, there's k+1 throats which are degenerate.
So then you've got, well, each of those saddles contributing an RT.
Yes, exactly.
So you k times the original.
Not quite. It's more than that. Like the non-cross, because now even replica symmetry breaking things become important. They're all degenerate. So there's actually a Catalan number of them.
Okay, and that's the 3/2.
That's where, so the degeneracy is the Catalan numbers, and in the large k limit that gives you this 3/2.
That you would have got, log k would have come even from that. Sorry, how?
Yes, absolutely.
K times
Absolutely.
RT form of that. E to the power minus n.
Because there's k surfaces. It's the same idea. It's no, because there's many saddles. So when you're computing trace rho r to the n, there's one saddle corresponding to replication at each surface.
Yeah.
Yes. Right. So each of those is a distinct saddle contributing to trace rho r to the n. So that gives you k of them. There's also replica symmetry breaking ones, which gives you the Catalan number of it.
That is okay, correct.
Correct, correct, correct. Okay. Good.
It might just be a sort of matter.
No. Well, you can think of it as a matter effect. Yeah. You can think of it as a matter effect. Yeah, that's fine. Yes. You can think of it as a matter, like one loop piece. That's fine.
Wait, is it going to come from Germany? I was thinking that.
Like it's.
So, yeah, maybe I'm wrong, but I thought physically isn't because of the matter things going in and they are factory.
Yes, but I guess the distinction is like they're completely different saddles about which these contributions are coming, not the determinant about a single saddle. That's maybe the distinction that's being drawn. And so FLM will give you that first thing, and you can still interpret this as, I would still call this a matter contribution, but I think it's different from FLM because of this thing. Yeah. Okay. Log K was guessable, just what Shiraz was saying was, so you have these. Exactly. The 3 by 2 comes from the Catalan numbers. I mean, the thing that Shiraz was counting was just the replica symmetric saddles, which would give you a log K. The 3 by 2 comes because of the additional replica symmetry breaking saddles. This is, for example, so the, yes, this is a replica symmetry breaking configuration. Like a simpler replica symmetric configuration would be something like that. Everything is doing the same thing. I have not included the wormholes yet. We'll get to that.
But yeah, when you say replica breaking saddle.
Oh, there's no saddle. There's no wormhole saddle in this case. I mean, okay. It depends on the delta and so on, but okay, at least in this regime where k is like much smaller than e to the 2s not over 3, they're completely suppressed. And then I'll say what happens when k becomes comparable to that. Okay, the same sort of issue. Okay, so just because Shiraz brought this up, let me also say this. So suppose we had different operators. So suppose instead of having all being the same operator, let's say we chose them to all be different. Then you would have something like this. So here, let me draw a situation where we have 3 of these operators. 1, 2, 3, 1, 2, 3. So this is just the density matrix of one of these. Oh, sorry. Yeah. The puzzle was that just a naive extrapolation of the semiclassical answer gives you a negative entropy, right? Like if k becomes really large, it'll compete with this S naught term and it's negative contribution, so it's going to become negative. So this is basically like decreasing, but it eventually goes to negative. You want something to come in and fix that. That's the key. Okay. Good. So here's the calculation of trace rho r squared for k equals 3. Right. So we have 1, 2, 3 insertions in one of the kets, 3 in one of the bras, and then they've been multiplied together. So we have this many of them. So now this situation is exactly what Shiraz was talking about, because now if you're considering all the different diagrams, there's actually only the following diagrams. So there's going to be diagrams of this type. So if we're considering non-crossing diagrams, the only thing we need to choose, so I can either glue them horizontally or vertically. And I have to do the same thing, and I have to do it in a non-crossing fashion. So if I glue, for example, if I glue 2 horizontally, I'm not allowed to glue 1 vertically, right? Because that would cross. So what I can do is I go from 1 till some number, glue them all horizontally, and then everything else is glued vertically. Those are the only diagrams that I have. That makes sense? I mean, I can say that again if you want. I'm just counting all the different possible diagrams we could get. Here, I'm assuming that there's no 2-point function between, say, 2 and 1. So the only contractions are between 2 and 2 and 3 and 3 and so on. And so I can actually draw all the 3 diagrams for you. The 3 diagrams are the following. Sorry, I drew that wrong. Wait. The second one is the first one turned around. Oh, yes. Okay, that helps.
First 3 is not surrounded, so we have 3 options about it not around.
The first 3, which 3? This 3?
3 surrounded by anything else. So we have 3 options to go 1.
Sorry, I was going to say that. So for 3, let's say we first choose it vertically or horizontally. There's 2 options. Let me just draw it systematically, actually. So once I choose this vertically, I have the freedom to choose 2 vertically or horizontally. I can do either of those choices. But I don't want crossing diagrams. So the different diagrams I get are, so once I've chosen 3 horizontally, then I'm forced to take both 2 and 1 horizontally as well, right? So that's one option I have. And then the other option was here, I could have taken 2 vertically, and then that would look like this. And I would, now one can be either horizontal or vertical. So I have this one. Wait, why do I have so many diagrams? I'm confused. It's like I have too many diagrams.
So all vertical is the same as all horizontal.
Oh, maybe I have 2 K diagrams. Yeah, there's. So yeah, the situation now is like we have different operators. So with considering that situation, I'm just giving a combinatorics of what those diagrams would look like.
In the context of any entropy or just
For the any entropy, So this is n equals 2 trace row squared for k equals 3.
And what is the operator?
There's 3 different heavy operators.
So O tilde is the product.
Okay, you can say that, or like it's O tilde 1 times O tilde 2 times O tilde 3. Yeah. Yeah. I think. Yeah, I think I might have miscounted this. Let's see.
Oh, sorry, why
Yeah.
it reflects every time? Should it not be
Oh,
1 to
sorry,
3,
4
1
is
to 3?
correct. Yes. Sorry, can you say that again?
No, I mean when you do like a trace row to the whatever square,
Yes.
it not be like a 1 2 3 1 2 3 and then finally only one.
No. So this is rho r. So rho r has 3 to 1 and then 1 to 3 because it's in the bra and the ket. This is time reversed, and then yeah. So I think 4 is correct actually. Yeah, that's right. So okay. First, when I chose 3 to be vertical, I had many options. So let me first choose 3 to be horizontal. Once I choose 3 to be horizontal, this is the only diagram I have. Then when I choose 3 to be vertical, then I have. Yeah, and then so if I choose 3 to be vertical, then 2 can be either horizontal or vertical. If it's vertical, then there's 2 more options, but let me first make it to be horizontal. That's more systematic, I guess. If I make it horizontal, then 1 is forced to be horizontal, so that's the only diagram you have. If I now, so now we have 3 is vertical, 2 can be vertical as well, now 1 can be either vertical or horizontal. So there's going to be this and this. So 4 diagrams. So 4 basically here, okay, I might have miscounted in my notes. There's k plus 1 throats, right? So this is exactly the factor that Shiraz was talking about. So because there was k plus 1 throats, the 4 different diagrams you have here are basically just the 4 different diagrams you get from replicating at each of the different surfaces. So this gives you k plus 1 terms. So trace rho r squared is just equal to k plus 1 times e to the s naught.
In this case, Chirag, log k complete is exception.
Yes. So basically, because in the second Renyi entropy, there's no replica symmetry breaking saddles. Okay. Good. So again, we can compute the entropy from here, and you'll find that, so let's say the second Renyi entropy goes like S naught minus log k. That was what is log k plus 1, but at large k, it's just log k. So that's exactly the thing that Shiraz was saying. Okay. So again, here when k is much bigger than e to the s naught, again you have a puzzle with negative entropy. Same sort of issue. So it's a quite generic puzzle. It'll arise whenever you have many of these, whenever you have these long wormholes with many Python's lunches and many extremal surfaces that are sort of comparable. Because S2 is minus log of because it's 1 over 1 minus n, right? So S2 is minus log trace rho r squared over trace rho r squared. Wait, where? This one? No, I think it's e to the s naught because this thing is e to the s naught squared. Yeah. Okay, good. So, okay. So now I've told you what the puzzle is. Now let's try to see how it gets resolved in the bulk. Okay. What are we doing on time? The puzzle is basically that if you take too many insertions, then the naive extrapolation of the semi-classical answer gives you a negative entropy. You want some other effect to make it positive.
And with S2, you can see it has to be positive.
Yeah, exactly. The Renyi entropy just has to be positive. All Renyi entropies have to be positive. So yes, correct. Okay. So now we're going to try to model this. Actually, so first I'm going to talk about a tensor network model for this. So it's a random tensor network model for this exact same effect. And in fact, it's going to be, this is not even a model. This is like almost literally doing the calculation that's happening in the bulk. So let me say how that goes. So we're trying to consider a situation which is a long tensor network where you have many tensors. So this is the left, this is the right. And this essentially is trying to model the fact that you have many different throats. So each of these tensors you can think of as the bulge, and each of the bonds you can think of as the throat. So it's sort of oscillating between each of them. Each of these bonds, yes. Yes. More generally, it'll be different. In the microcanonical case, you have to account for it. Yeah. But the key point is that eventually the combinatoric factors are going to overwhelm all of that and give you a negative answer.
No, but combinatorial factors, why would I care about those? If you only short guys dominate, at least when they are distinct, then there's probably some.
No, the replication is because of this fixed energy boundary condition, it's always going to give you an entropy that's given by the area of that surface.
No, I mean, let's say you want to do this counting and now just make sure that all the propagators, not just are crossing, that don't cross, but also are the shortest possible. Right?
Yeah, I'm saying that that's not going to be the accurate description because I think eventually they're going to be all degenerate. Like that's just coming from the fact that basically replicating about each of these surfaces is going to give you the same action.
Why is it that I should just look at the chart? I mean, why is it that all these diagrams that you view contribute the same? It's like those ones contribute less than the
Which ones? Those ones?
those are longer probably.
They look longer. They're not longer because it's fixed energy, right? Like it looks.
Fixed energy means those intervals, individual intervals are constant, right?
Yeah, but it looks like this. I mean, maybe that's a misleading picture. The picture looks like, So the way we drew it in the pets case was something like that, right? So
Yeah.
something like that. And then I'm just saying like, this is what's happening. This sort of thing. Let's see some other diagram.
It might be that it's like a more like a flower structure there, but still quite like on the line.
Yeah, you might be right. Let me think. So what we're fixing is the boundary condition being the energy at the boundary is being fixed. So no. We're just fixing like that. You can't fix that as a boundary condition. We're just fixing something at the asymptotic boundary, which is just the fixed energy boundary condition, and then you just fill it in with whatever. Yeah. So here, yeah. Yes. Yes. I guess Abhijit is saying that's not manifest. So in a fixed area calculation, I think that is manifest. That's what the tensor network is going to do. I think maybe Abhijit is saying if it's a fixed energy boundary condition, it's not manifest that that's true. And that might be correct. I believe that. Sorry? No, all of them have the same area almost by construction. But when you replicate, then whether all of these diagrams contribute equally is the question. And would be surprised if they. It could be this subtlety between fixed area versus fixed energy. Yeah, certainly, if it was fixed area, then you agree that it's just replicating about that surface, so it's just picking up that action. Okay, yeah, I'll think about that. Okay, so here what's going to happen is more like the fixed area calculation. So here it will work out. And so what we're doing here is taking a really long tensor network, and the number of tensors here is k tensors. So that represents the k bulges, and there's going to be k plus 1 bonds connecting them. That's representing the k plus 1 throats. Each of those bonds is taken to be of size d, and this is not even the, and each of these tensors is picked randomly. So this is T1, T2, T3, and so on, and they're all picked randomly. And this is not even that much of a model because you can just think of T1 as the operator PBPS, O1, PBPS, or whatever projector that we're using. So this is expected to be a random matrix, and that's exactly what this tensor network is doing. So it's like almost literally a rewriting of the boundary state in a way that is manifestly like the bulk slice. This is one example where, yeah, we're going to take all of these to be Gaussian. We're not taking it to be, yeah, we're going to take it to be Gaussian random to mimic the fact that in gravity that's what's going to happen because of this Catlin number counting. Yeah. Because these are expected to be random matrices. Good. Okay. In fact, so this is almost exactly how Chandra and Hartman constructed their tensor network. So they did it in ADS3 CFT2, and they had literally this sort of a tensor network, which they explicitly constructed from CFT operators, and it was basically the same sort of idea. So this is quite an accurate model of what's happening in the bulk. And now we can do the same thing and try to compute. So we can try to compute the Renyi entropy. So before we compute the Renyi entropy, we need to distinguish between a few things. Since we're doing this, we're picking random tensors, we're basically doing averages over the Haar measure. And since we're doing averages, we need to be careful about what's the quantity we're going to compute. Yeah, isn't that called Haar measure? I actually didn't. Yes. Yes, the remission. Yes. Okay. Yeah, so basically just integrating over, like the tensor is some state on these two legs, one of which is being contracted, and that state is being chosen from the Haar measure on the product space of two bonds. That's what I mean. Yeah. Okay, so yeah, since we're computing averages, we should be careful about which quantity we're computing. So there's 4 options we have essentially. The first quantity we can compute is the annealed Renyi entropy. This basically means computing the following. We compute the average of Zn divided by average of Z1 to the power of n. Let me just first write down all the quantities and then we can discuss the different properties of them. Then there's something we invented which is called the semi-quenched Renyi entropy, which is the following. Now we just average Zn and divide by Z1 to the n averaged. So now the factor of n is inside the average. Then we have what we call quasi-quenched, which is the following. It's Sn Q Q, where we take this whole quantity Zn over Z1 to the n, the whole thing, and then average that. And finally, you have the full quenched Renyi entropy, which is 1 over 1 minus n log Zn over Z1 to the n, the whole thing averaged. There's 4 different things we can compute depending on which averages we care about computing. Yeah.
Averages are over couple constants.
So in this case, I'm just talking about the random tensor network. So here we're picking these tensors Haar randomly. So it's an average over that. It's a Haar average over the choice of. In gravity, you should think of the tensors as these operators. Yes. Yeah, so here we're trying to think of these as modeling like large delta operators, which have then been projected onto the BPS sector. So you can imagine like different operators being projected onto the BPS sector, giving you slightly different. Correct.
These operators then talk about the boundary operator.
Yes, this is also a boundary operator.
But now why keep them in the bulk?
Good, that's exactly the point. So this is exactly how the ADS-CFT, this is the main reason why people think that ADS-CFT works somewhat like tensor networks, because what this is doing is it's giving you a preparation of the boundary state. This is representing the Euclidean path integral, which it's some discretization of the Euclidean path integral, which is preparing the boundary state. And it's also at the same time representing the bulk geometry. So it's doing both.
But think of this line as this.
You can think of it, good. So you can think about it in this way. You can think about the tensor network sitting here, where each of these is like a tensor. Yes. Yeah.
Here just some doesn't matter, right?
No, it will matter. It will. I'll say why it matters. So I'm going to say that this is one way to think about the tensor network, but another way, which is what ADS-CFT is telling us, is to think about it here, where now you think of each of these as the throats and each of these as the bulges. So it's representing both of those slices. Yes, it's in that spirit. Yes, Cauchy slice holography type thing. But this is much older than that. Like this is like initially how people thought about the Mera tensor network and all of that. Like there's an isometry relating like different slices here, all of which look like hyperbolic geometry, and maybe Omkar wrote a paper about this. Yeah. So it's in that spirit. Okay, so then we want to do this average over these random tensors, and this model is literally the thing we were computing before actually, because here also we considered all of these different operators and computed the Renyi entropy. So the calculation is almost identical to what we did for. So the naive answer. So okay, first let me say what the properties of each of these different quantities is. The annealed entropy can be negative. There's no particular reason that it has to be positive, and in particular limits, it does end up being negative. This is something that has been noted previously. So most of the time when people talk about annealed and quenched entropies, they talk about the thermal entropies. We're sort of extending that to the situation of Renyi entanglement entropies, but the same idea holds. where this thing can be negative as long as, yeah, in certain situations it can be negative. This thing, on the other hand, has to be positive because what we have here is, so for any particular member of the ensemble, we have trace of rho to the n is less than equal to trace of rho whole to the n. So now we can also take a positive combination of them. So the average of these also satisfies this, which means that which means that this thing is positive. Basically, we're just taking the ratio of these averages. Similarly, these two quantities are also positive for the same reason, because each of these quantities is positive in each theory, and then we're just taking an average over that. So, however, so this thing is a bad quantity to compute. These things are good quantities to compute, but there is an issue with these two quantities. The issue with these two quantities is how do you compute something like Zn over Z1 to the n? The way you do it is by a replica trick. So these two need replica tricks. So for example, here, what you can do is try to compute something like Zn, Z1 to the m averaged, and then take the limit of m going to minus n. So it's some analytically continued version of the product of partition functions. And similarly, for the log, there's what's called the no replica trick, which is you take the limit of p going to 0 of Zn, Z1 to the m to the power of p minus 1 over p. So there's replica tricks that are designed to obtain these two quantities. Now, the reason this is not as often discussed is because most of the time in gravity, these are self-averaging quantities. So no matter which one you compute, they all give the same answer. So if you do Lukowitz-Mardasena, usually we just do this. We just compute the disk partition function with n there, and the disk partition function, like the usual disk partition function, just take the ratio of that. That is the calculation we did above. So the one way to say what we did so far is we computed, so the reason we ignored wormholes there, one way to say it is we were computing the annealed entropy. In the annealed entropy, you're computing the average of Z1 and then taking the power of n. This is also a gravity calculation. There's no difference. I mean, the gravity is computing some coarse-grained average, right? Like there's.
That way, Euclidean gravity is what you.
Yes, so if I choose Euclidean gravity, yes, so if I choose Euclidean gravity, then I can compute different things. I can say, let me compute Zn as computed by the Euclidean path integral and divide by Z1 as computed by the Euclidean path integral to the power of n. And that's exactly what we're doing. I don't need to say average, but that's exactly what I'm computing. And in that thing, because I'm computing Z1 averaged doesn't have any wormholes. There's just a single boundary. The boundary conditions for Z1 is just a single circle.
No.
That,
1 to the power n.
but I'm not averaging, I'm not computing the path integral for Z1 to the n. I'm computing it. It depends on which quantity we want to compute. Like that's this quantity. That's this quantity.
Well, I mean, makes sense when you have an average. But if you talk about this.
No, I mean, I can, instead of these bars, just think of the bar as gravity path integral. Forget averaging.
Yeah, then I would consider, you are given n disconnected boundaries, and then you are supposed to do a gravitational path integral.
If I want to compute this.
Average thing.
No, like just replace the bar with path integral. Like, what's the difference?
But then yeah, they should be done that quantity.
What do you mean should? Like, it depends on what I want to compute.
That's what Euclidean gravity tells you, right?
Euclidean gravity gives me rules for computing each of these quantities. I can compute whichever I like.
That's with some understanding in mind that there is path integral computing some average.
No, I don't need to say that. I mean, it sort of manifests from here that it's going to compute some sort of average because these quantities are going to be different. Like only one of them will have wormholes and one of them won't have wormholes.
Well, that's like constructing a quantity that won't have a wormhole. I mean, if you have
no.
boundary,
I mean,
you're supposed to compute the partition function with those boundary conditions.
Yes.
Well, compute all the patterns, all the gravity.
Yes, and I'm saying for this quantity, that the thing is there's just one boundary and there's just only the disk. There's no wormholes. The boundary conditions for computing Z1, forget bar being averaged, is just a single disk. There's no wormhole. No, but I do. That's this quantity. That's why I'm trying to distinguish these quantities.
They have a bar on that. There is no bar.
Bar here, let's say bar means computing the gravitational path integral.
Why is that? If you are computing
I'm defining it that way. I'm defining a quantity.
definition.
Yes, but I'm just saying these two will give you different answers. That's what I'm pointing out.
That I agree, but in the Euclidean gravity case,
Yes.
not that was an artificial restriction.
No, what is an artificial? I mean, these are just different quantities. I don't understand why it's artificial.
You can call that, that's what you computed, but what you should have computed is the last thing.
Yeah, in principle, you want to compute this. Why even this? Why not say this? I mean, it's the path integral where you compute log of z1 over zn over z1 directly.
What is the path integral?
It's that replica trick. Let's forget about ensemble. Like, I think this word is becoming controversial. I think let's just say bar means gravitational path integral.
Okay.
Then these are four different quantities with four different boundary conditions.
I don't know the meaning of the other quantity.
You need to do a replica trick to get them. You compute something like zn times z1 to the m, then take m to minus n. Is obviously an ensemble. Yes, that's also true. There it's clear. But I think I'm saying this even more generally. Yes. You might worry that there's other things that like contribute and so on. But if you, let's just say you had some well-defined gravitational path integral, you don't know a priori whether it's computing an ensemble or not. I'm just saying, let's define these quantities where the bar means compute the gravitational path integral. If it has wormholes, then it will be an ensemble. If not, then not.
I mean, I see that if the only point that you're making is that it is effectively what you ended up computing is the first quantity, and that's why it was negative.
It's not just me. We always compute the first quantity. Like Lukowitz-Maldacena computes the first quantity. That's what I mean. And I'm just saying that in that situation, the negativity of the entropy is not actually a problem, as long as you have an average, as long as you interpret the gravitational path integral as some average. On the other hand, these other quantities do have to be positive. The difference, so Zn, you can think of, let's take this just the case of like thermal entropy or something like that. Then Zn is like a circle, single circle with length n beta. And Z1 is just a length beta, and there's a product of m of them. Yeah. Okay. Okay, good. So what we're going to do is, so this is of course a quantity that can be negative. So what we found earlier is perfectly consistent with the fact that this can be negative. These quantities are in principle what you want to compute, but in order to compute them, you need some replica trick and you need to then analytically continue. That is in general a problematic thing. That in general won't, there's some subtleties with the analytic continuation, which makes these quite problematic, and this is like quite prevalent in the literature. So this quantity is going to be useful for us because here, at least at integer n, there's no analytic continuation that's needed. We can just literally compute this quantity.
Sorry, 1 o'clock. Administrative meeting, I cannot miss.
Oh, yes, I will be. Yeah, okay, no worries. Yeah, so good. So that's why we're going to focus on computing this quantity, just because it does have a positivity property. So it is required to be positive, and the naive answer that we obtained before would have made it negative. Whereas these quantities require a replica trick, and that has some subtleties which we're going to ignore, which we don't know how to resolve. Correct, exactly. So that's going to be the point, and Abhijit said that earlier as well. The key difference between the first and second thing is whether we average after taking the product of disks, or whether we just take the average first and then take the product of n. B is from D. Yeah. There is something I will comment on in that situation. So what we're going to find is that B is actually a very non-self-averaging answer. D will be a slightly non-self-averaging answer, but in some sense less than B. Yeah, we'll see something related to that. How long can I go on? Yeah.
The group understand you say you compute the first thing.
Yes.
That is because the connected saddles are put down,
Correct.
right?
But you could have complained there itself. Why didn't you include this
No, I
wormhole?
couldn't, because I know that the connected saddles are put down.
Yeah. So for the
But it was
previous
not
thing,
obvious that- that's why.
yeah. So I agree with that.
Part then comes all this, right?
No. I don't agree with that second point. I think these are just different quantities. You can compute all with the gravitational path integral. Why would you compute B? Yeah. So why would you even compute B? Why not just compute D? I think you will say even B is the wrong quantity to compute.
Why
Because why should I average them separately? Why not just the whole thing?
not average, no averaging.
Why shouldn't I compute the whole thing at once with the? Yes. But why not compute log of trace rho to the n divided by trace of rho whole to the n all at once using the gravitational path integral? That's a different thing. We're going to find that these are different things.
We just suppose compute trace rho to the n separately and then trace
Why?
power n.
Why? Why shouldn't I just compute the whole thing at once? Yes, but I think he's not happy with that. So let's.
Gravitation part should pick a particular one. It tells you what exactly you need to do. I thought it is the B quantity.
No, why? Why? Yeah, it depends on what you're computing. No, you compute log of Zn over Z1 to the n. That's the quantity. Yes. That I'm going to say that, but yes. Okay, you can say that. Yeah, yeah. So that's why I was trying to distinguish between these quantities. B is easy to I'll be able to do a computation for B and show you that it's fine. C and D, because they need this replica trick, it's subtle because of this analytic continuation, and there's no controlled calculation we have or anyone has in the literature of those two quantities. So it's not easy to say it's fine, but since I can convince you B is fine, maybe you believe C and D are also fine. That's A is never fine. There was no reason for it to be fine. Like it could be negative anyway. That was the yeah, exactly. So the key point is going to be what wormholes did you need to fix the answer? That's right. Yeah, so it's basically it happens when you when you zoom into the edges of a spectrum. So essentially what happens is when you zoom into the edge of the spectrum, since it's a continuous function, so whenever you're approximating it by some continuous spectrum, like the semicircle has some edge, the average density of states at that point is going to be less than 1. Right? So there's going to be less than 1 state on average, and that's the situation where you run into these issues, when that becomes important. When the fact that it's a situation where in principle you need a discrete spectrum, but you're approximating by some continuous thing, and there's an error in that. So this also happens, for example, when you try to compute the thermal entropy in JT gravity and so on. Like when you zoom into really low temperatures, though you zoom into the edge, then it's exactly this. And I'll make a connection to that. Okay. Are you happy with that? Okay. Okay. Good. So we're going to focus on this B quantity, the semi-quenched Renyi entropy, and let me try to compute it in the random tensor network and show you what happens. So the random tensor network, I won't review the whole thing, but essentially what happens is when you do the R random average, the calculation in the random tensor network becomes same in the limit where we take D to infinity, just becomes the same as finding the ground state of an Ising model. So essentially what you have is this quantity that we want to compute. So let's say we want to compute Z2 averaged. Z2 average is given by a sum over all possible configurations. Yeah, I don't know how to write it. So we can think of, so it's going to, in general, Zn is given by a sum of over all configurations, where at each vertex, we have all possible permutations. and we sum over those with some particular weight. So in the case of Z2, there's only two permutations. There's the identity and the swap. So I'm going to write it down as each vertex being either up or down. Okay, so it's basically exactly the Ising model, with the condition that we have imposed some boundary conditions at the ends dictated by the quantity that we're computing. So this is some e to the minus I of G, where this I is given by a sum over edges. Yes. Yes. My calculation of Z2 was also not correct, because that also in principle has wormholes, and that will be important. It doesn't fix the issue, as you're saying. Like, it only makes the issue worse, because these are all positive contributions in the numerator, and they make the real thing is Z1 squared. Yes. Yes. Correct. So you have a contribution which is log D times the distance between Gx and Gy, where Gx and Gy are just up and down. So we have this long chain. So we have this boundary condition of, let's say, up on one side and down on the other side when we're computing Z2. And we have a choice of how do we fill in this lattice, right? And so essentially, the simplest configuration is one where you just put in ups until some point and then downs beyond that, right? So there's just a single domain wall, and the only cost then comes from the domain wall where these are separated from each other. That is the leading order calculation that you do. So what this does is basically gives you the RT formula, because it's computing the area over 4G at each bond. But here, because there's so many degenerate bonds, you can have the RT surface be here or here or here or here. And there's going to be k+1 locations where it can be, because there were k+1 throats. So in that case, the answer, the leading answer that you get is the same as what we saw there, which is just k+1 over, so Z2 averaged at leading order just becomes k+1 over D. Again, you see that if you take k really large, if k becomes comparable to D, then this quantity can become larger. So this is Z2 average over Z1 average squared. This is like the thing inside the log. So you see that this quantity can become more than 1. And then when we take minus log of that quantity, it can be negative. So this is basically the same as the naive answer that we did. So this is the usual derivation of RT in the random tensor network. But of course, now we know that there's other configurations that we needed to sum over. And these you can in some way think of as wormhole-like contributions in a way that I'll make clear now. So let's think about what the subleading contributions are. So now we're going to take a limit where we take k to infinity with k over d fixed. Okay. So what are the sum? What contributes to Z2? Z2. So Z2 firstly has all of these configurations, which are there's a single domain wall. There's k+1 locations where we can keep the single domain wall. So we have k+1, choose 1, and that came with a weight that was 1 over D. Then you can have multiple domain walls. So instead of having one domain wall, you can have 3 domain walls. So that's a situation where you have up, then down at some point. So there's first domain wall here, then another domain wall here, and then another domain wall here. It's going to be 3 domain walls. And similarly for every odd number. So there's going to be this, and this will, because of these extra domain walls, there's going to be additional factors of 1 over D that show up. And it's going to be 1 over D cubed, and k+1, choose 5 over D to the 5, and so on. So in the limit that we're working in, you can resum this whole thing, and it just becomes sinh of k over D. Okay. Yes. So D is the bond dimension. So it's the size of the Hilbert space there. Gx and Gy are like the different permutations at each of the locations x, y. So x and y are labeling vertices on that graph. And at each point, you have a choice of permutation, which is just up and down in this case. So the distance between them is basically 0 if they're the same, 1 if they're different. Yeah, I'll say that. Um, let me just finish the calculation and then I'll say that. These boundary conditions came from the fact that we wanted to compute trace rho r squared. So the way to do that is with a replica trick, you take 2 copies of the tensor network and then you apply a swap operator on the right side. Then you do the trace. So what that's going to do is just trace the left-hand side trivially. So this up is representing the fact that there's an identity permutation there. And here you have a swap operator. So that's represented by this down. These are the 2 permutations that you have on 2 objects. So since we were computing trace rho r squared, what you do is you take rho, tensor rho being full rho, not rho r, and then you compute a trace with a swap operator on r. So the fact that you implemented a swap on r and identity on the left shows up as these boundary conditions. So the down here is representing the swap and the up is representing the identity. Because we wanted to compute trace rho r squared. So maybe you can draw a pic. Does that make sense? Like you're just swapping these two, and then when you then trace, then they'll glue with each other just to implement matrix multiplication. So as Onkar was saying earlier, like so these wormholes actually make the situation worse. Like sinh k over d is even worse than k over d that we had to start with. So it makes it worse. So then we also look at z1 squared. The calculation for z1 squared is similar, but now the boundary conditions are up on both sides. So we have up here and up here, or maybe we can say, yeah, up here and up here. And then you can fill it in with whatever possible configurations. The leading answer, of course, is where there's no domain wall, and that just contributes 1. So when we compute z1 squared average, is just 1, which I can suggestively write as k plus 1 choose 0. And then similarly, again, we're going to have the situation with 2 domain walls. So where we have up here, a few downs, and then up here, so on. That's going to be k plus 1 choose 2 over d squared, and so on. When you resum this, you'll find cosh k over d. And so the Renyi entropy is actually given by minus log of the ratio of these 2 things, which is just minus log tanh of k over d. So if k over d was small, then this can be just approximated by, this basically just gives you log d minus log k. But if it's large, the important point being tanh is always smaller than 1. So minus log of that is always going to be positive. Okay, that's the important point. So now let me say a little bit about what this means in gravity. This is the, yeah, so here I was calculating z1 bar squared, and this is Sn semi-quench. Thanks. Yeah. Yes. Correct. Good. So now we can just give this. So the important wormholes, as Onkar was saying, is these wormholes. These wormholes are the ones that increased the denominator and made sure that the entropy turned out positive. What do these wormholes look like? These wormholes, so in gravity, z1 squared is computed by boundary conditions, which are the product of 2 disks. The leading answer was something like that, right? Where, so there was like particles 1, 2, 3, 4, and so on, and there's 1, 2, 3, 4 here as well. Okay, so these are just glued together trivially, but then there's other, and both of them are glued trivially, so that's the leading answer. So it's the product of these 2 disks, plus the first leading correction. So this pattern, so there's a d squared and d to the 4th and so on. D you should roughly think of as e to the s naught. So this is basically in powers of e to the minus s naught, so e to the minus 2 s naught. So it's basically a genus expansion. So this is going to look as follows. It's going to be some situation where you have a wormhole and you glue some of them straight, but then you want to glue something horizontally. So let's say you wanted to glue these 2 horizontally. That would be a crossing configuration, and that would count less. So instead of gluing them horizontally, you actually glue them to the other side. So there's going to be many such things that you glue horizontally across the wormhole, and then the middle stuff you glue vertically.
So not just that it's crossing configuration, it's just not possible.
No, it's possible. It's possible, but yes. Yes. Correct. And then depending on the number of domain walls you have here, there's a minimum genus in which you can draw it without crossing, and that's going to be the set of wormholes.
One boundary.
Yes.
That's all the places where the second mode can appear.
Second.
This is one diagram where all of the terms are particular. The second boundary could be like placed in between any of those modes. You also count it.
You mean the wormhole configuration, which looks like that? Like it's a cylinder-like thing? Yeah. Yeah.
The second boundary could be here or here. You also distinguish those. You understand my picture, right?
Yeah, I think I understand your picture. You're saying there's a connected thing which is like that.
Yeah, because these lines can't be become.
So you're saying it's basically a connected thing like this. Is that correct? Is that the picture you have in mind?
Yeah.
Yeah. So the tensor network calculation doesn't see that. Doesn't see any wormholes of this type. So what I did here was did a literal calculation in the tensor network, right? And then I'm just trying to give it some gravity interpretation. The thing that the tensor network counting is just it doesn't have any extra contribution for something like this. It's not so clear to me when you include non-perturbative effects. Like at the disk level it is. At the disk level it is, and that's why you saw the Wigner semicircle come out of it and all that. Once you include 1/n corrections or 1/d corrections here, there's something else that's natural from gravity, as he's pointing out. Like this is a natural contribution from wormholes, whereas in the tensor network you don't have anything corresponding to that. There's other configurations with the tensor network is seeing, and those are the ones that are getting counted, but these other ones aren't getting counted.
So what is something?
He's suggesting a situation where you just imagine that you're. Oh, sorry. Maybe this is related to what Abhijit was saying. There's no non-crossing diagram of this type, right? Because is there? Oh, maybe there is. Sorry. Yeah. So you're not counting those diagrams. So there's a cylinder, and you could, in principle, draw like all these vertical lines on both sides, and that's a contribution that the tensor network is not seeing. So in principle, maybe that's also related to the fact that we're treating it like a Gaussian random matrix, but in principle, these wormhole corrections involve like, there's a full genus expansion in the potential itself, right? So those effects are being ignored. I guess if you're more careful about what the potential is, then even the tensor network calculation would be different. Yeah.
But this would be subliminal, right?
This thing? Yeah, I think you're right.
Precisely by the amount which allows for a non-crossing.
Yeah, I think you're right. This is right. The reason these contributed comparably. Oh, yeah, that's right. So the reason these contributed comparably to the product of disks was because there was a genus suppression, but a combinatorial enhancement. And there's no combinatorial enhancement here. So it's not important in that scaling limit. The first one, the one you suggested, which is just a cylinder where it's just vertically glued on both sides. The combinatorics is the same as the product of disks, right?
There are so many of those diagrams.
What's so many? Like you mean just the integral over all of this?
There is one dominant one. In theory, it may look like there is some more, but so
This being the second boundary, it could be in between any of the two codes, right? You could place the second boundary.
What does that even mean? Like this is some extended thing.
that is what lines that you.
Oh, like where it goes on the cylinder. Oh, that side. I see. Okay, good point.
The second one, you could.
Yeah, those aren't getting counted. Yeah, those aren't getting counted.
The large clip of that one.
It's big, right? Like it's K. I think it's just K. I think it's just K squared, maybe, like from both the sides. Yeah, that's a good point, actually. That I think it's important. Because, yeah, there is a combinatorial enhancement. So it will compete. Yes.
Even with two operators, there are three diagrams, three different choices of taking the second boundary.
I thought there was going to be 4. Oh, sorry, 3 on one side, because you can do the same on the other side.
Each of the 4 of them, each of the 4 you counted initially.
Yes. That's on one side. That was also for the Renyi entropy. So that was like different. Here, the only possibility is gluing this way. But the thing you're pointing out is if I look at it this way, so the way you're drawing the diagram, let's draw it as an annulus, right? So if you draw it as an annulus, you can comb these this way or that way.
Yeah.
And
This thing.
no, that just means combing this way or that way, right? That's a full counting of it. So that's maybe one way to say it. And so k squared is because you can comb this anywhere, like you can, the ith one can go to the left and the I plus 1 can go there, and same for this. So that's why it's a k squared. So it is combinatorially enhanced. And so yes, the tensor network is missing that. It's a natural thing in gravity, which is missed by the tensor network. And that's related to what I was telling Onkar, which is we're just treating this as a Gaussian random matrix, but gravity has other corrections, right? So these genus corrections are non-Gaussian corrections. These would make it better. Yeah, yeah, they would make it better. Yeah.
What is Z2 bar?
Z2 bar. Oh, Z2 bar is a circle with 2k insertions.
Yeah.
4k. No, 4k. Oh, yeah, sorry. So here I just talked about Z1 squared. In that case, it's a single, yeah, good. So in Z2 bar, it'll look like, yeah, exactly, homogeneous connections. Yes, it's just handles to make it non-crossing. Exactly, that's right.
Yeah.
Oh, okay. How long do we plan to go on? I can stop at this point, like there's more to say, but no, I had like, so in principle, I had like 7 parts and I'm in part 3. So, so this is actually a natural stopping point. I was going to start part 4 and maybe it's not worth doing that right now. So I'm also hungry. So I'm here till tonight. Yeah, okay. Yeah, thanks.